Where are we? Let's see. D. Question D is asking. Is it D? Yeah. All right. So suppose the agent expects both daytime, evening. So this time we are considering daytime and evening calls. At what point will she be indifference between plan A and B? So we're looking at this time A and B, not A and C or B and C. Okay. But it's not just minute, but look at the percentage of call minutes for daytime calls, meaning that which plan is better by how much. Okay, I think that's what it's asking. So we need to solve for plan A and B using, in this example, here we go. We can set up as a daytime with a D, evening time with a E. Okay, so 20 plus 0.5D plus 0.2. So just as a, the case presented, we set up the formula just like that. Same thing, plan B is 55 cents and 15 cents. But the only difference is just adding the D and E so that we can solve for D and E. And we make an equation. So each side set up that, and we solve for D and E, just algebraic, manipulation, if you recall. And coming down over here, D equals is this right? I think a little bit mixed up. This is a little bit weird. Yeah, it is right. Yeah. And then it's coming down to 0.5 E. Okay. Meaning that if you have 100 minutes for evening time, then daytime will be 50 minutes, right? Because it's only half of them. Okay. So what's the fraction of it? What's the percentage between evening time and daytime? You have to add both evening time, daytime to end up 150, right? So 50 over 150 is 1/3. So conclusion is, because it's 33%, so add 33% of total call minutes made in daytime, and will be no difference between plan A and B, because we solve for the D here. Okay. And if you're not sure what exactly, how we exactly come up with, you can actually play with the actual minute, starting from 1 minute. One is too small, I guess, starting from maybe 100, 200, 300, 400. If you increase by that, then you can build up, columns, 2 columns and 3 columns. Then you'll see the difference, how those numbers are increasing, and find out that will be only 33% because it end up having 0.5 E for D, which is a daytime minutes. So I think it's kind of remind you of those math problems in high school. Any questions? We good?
I'm good.
Okay, great. Number 3. Okay, this one is interesting. So we have a situation need to buy machines, and 2 type of machine. Type 1 with 10,000, type 2 $14,000. However, we have a workload to fulfill, right? So we have 3 productions going. And first product, just like that. Second product, annual demand, processing time. Then third product, okay, annual demand and processing time per minute, per unit. Okay. So there are serious questions we're going to answer. So basically we can sum up the questions here. So we need to buy a machine to make those 3 products, okay, either type 1, type 2, not at the same time, okay. You're going to buy one or the other. And each type works at a different speed, as we can see from the example. So there's some concept we need to understand. Workload, that's how many minutes we need to make all the products for the year, that which is given right here. That's the workload. And then capacity, how many minutes a machine can work in a year, that depending on the machine type 1 or 2. And how many machine we're going to need it, that just use those 2, workload and capacity. And if you take a workload divided by capacity, then you know how many machine you're going to need it. Then there's a cushion, idea of cushion, capacity cushion. So that's for the safety, and just in case, or you're running short. If you have a little bit of leftover, that's good. But if you have too many of, those things are left over, that's no good, because you're losing some of those costs. So capacity cushion is there to calculate. So that's the capacity minus the demand, or a workload, I believe. Some workload that need to be completed. And total costs. So at the same time, the cost of machine and maintenance or running the machine in this example. So first question is how many machines we need to each type in a year, how many extra time we have left. So let's take a look, okay? All right, so the condition we have is 8 hours per day, 250 days a year. So the minute we're going to calculate per machine, just take that 8 hours times 60 times 250, that will be 120,000 minutes in terms of minutes. Costs, which is given, so each of the type 1 is 14,000, type 2, type 1 operating costs, purchase cost of type 1 is 10,000, type 2 is 14,000. Operating cost for type 1 is $6 per hour, type 2 is $5. Okay, those are the conditions that we're going to work with. So we're going to find the workload, that how much we need to work for entire year. Okay, then we can find out how many machines that we're going to need. Type 1 of workload, in case you're using type 1, then product 1 the other way around. Okay, So annual demand for product 1 is 12,000, which is right. Then you need 4 minutes. Okay. So that's where it comes from to find out the workload. Okay. And the product 2, 10,000, 9 minutes. Product 3, 18,000, 5 minutes. Okay. So that's how we have come up with 228,000 minutes total. Okay. And type 2, going back, let's take that same annual demand, but this time 6 minutes, 9 minutes, not 3 minutes, and end up 216,000 minutes. Okay. So capacity for machine will be, we just calculated that in terms of minutes, which is 120,000 minutes. Then you divide the total workload for type 1. So how many machines you're going to need, because that's what we need to complete. That's the capacity for each minute. That's only you can achieve, but you need to achieve entire 228 minutes. So you need 2 machines. Type 2, you're going to need another 2 machines. I think it is end up having 1.8 versus 1.9. So you cannot have 1.9 machines, right? So you round up, you're going to have 2 machines each. Okay. And here's the idea of capacity. Oops, there's a typo. Capacity cushion. Okay. Capacity cushion is again how much time left after doing the work, so that just in case you need extra, then it'll cover, right? So capacity is 240,000 minutes. However, the workload we have is, much lower, which is 228. So left over is, 120,000. I'm sorry, 120. 12,000, I'm sorry, 12,000 minutes, right? And type 2 come up with 24,000 left over, okay? Again, that's coming from this number. That's the workload. And to subtract it from the capacity, then you'll have 24,000 minutes of cushion. So in this case, we have a kind of better cushion or higher cushion for type 2 because we have left 224,000 minutes, okay, if you're working this way. And that's what I work on in terms of just based on type 1, type 2, and based on capacity cushion. Then B, which type you're going to pick if demand is uncertain. That's, I think, is just judgment call based on the calculation what we already did. So we don't have to calculate this, just looking at the number and depending on the situation, why there's a demand. If you think demand is, steady, and otherwise, what you're going to do. So because one has a higher cushion and the other one has a kind of lower cushion. So depending on the situation, you can decide which one you want to choose. See which type is the cheapest when you include buying and running them. I think there's more numbers we need to understand. Yeah, okay. So the machine price is given, but operating cost is extra. $6 for type 1, $5 for type 2. Okay, so that's something we need to calculate it as well to find the total costs. Okay, $6 and $5. So we're gonna do the type 1 first. Purchasing costs end up 20,000, just like that. And operating time that we need to calculate, which is, we have it already, 228 minutes. And we want to convert to the hours, right? Divide by 60, and we have 3,800 hours. Operating cost, which is $6 per hour. So just multiply that, then we'll end up having 22,000. And total costs, add those two costs, which is machine cost and operating cost. Same thing for type 2. Okay. Finding out purchase costs and also finding out operating costs. Add them up. Then you can compare the total cost for type 1 and type 2. All right. So any questions or you want to go over other steps if you need it?
I'm good.
All right. What about the last one? What is it? Last one. This one, right? Capacity. Let me make it bigger. Capacity diagram. Okay. I think we have a few examples in the textbook, and including bottleneck. As I think it's something to do with the bottleneck in this example. That one of those point is kind of too small to digest all those incoming units, so that you cannot proceed, those amount you're supposed to process. So question is, what is the capacity of this system? Any idea? So how much capable of this system itself, given those two different, routes? But ending up, you need to go through 7, right? Station 7. Station 7 can handle only 20, right? So what's the capacity look like?
Are we saying that each one of these points, like 1, 2, 3, 4, 5, 6, has a specific capacity per hour? So at 1 we have 18, and then 2 is 15. So are these? Do we sum these? So 18 plus 15 plus 16, or
Right.
I don't.
Right. You're right. Yeah. Because that's basically the workstation go through, right? You need to process 18. You're going to process 18, 15, 16, but they end up having like how many? 40 something. However, station 7 can handle only 20 units. Same thing from bottom row, 17, 15, 17. But it can, again, it end up station 7. You cannot get away 7, right? So 7 is kind of bottleneck, meaning it can handle only 20. No matter how much it's going to coming to 7, that's all they can do.
So yeah, I don't know if I follow, because So if we start at 1
Mhm.
and we're saying that station 1 can handle 18 units,
Mhm.
does the arrow mean then those 18 units pass to station 2 and now they're 15 because station 2 can only handle 15? Or
Right.
can we use like maybe explain in a real life scenario like what this is? Like, is this a conveyor belt and these are like individuals working on some type of, I don't know,
Exactly. Yeah,
product?
that's right. Yeah, that's right. Yeah, just like a conveyor belt, right? And let's say you want to produce a keyboard, right? 18
Mhm.
units. Okay, number one. Then you're gonna process those number of keyboards with certain keys on unit, station one. Then you're gonna pass through number two, but you can handle only 15. So three has to wait, right? Because you can handle only 15 on station two. Same thing. It's gonna go through station three, but the station three can handle only 16 as well. So those units cannot handle because of limit on next station. It's going to accumulate it and it's going to slow down. Eventually, it's going to go through, of course, but it's going to take time. So it doesn't give you all, necessary scenarios, but the idea is trying to pinpoint where is the bottleneck. That's the pinpoint. Of course, if you want to make it really a good scenario, it's going to give you all the variables, how many people work in each station, how many hours, price, different costs and all that. But this is just kind of summarized so that we can kind of point where is the problem so that we can fix or we can improve the flow of the system. So if you have two rows all the way across, but there will be different story. But those two rows meeting into station 7, which is only one row meeting together. So that's why station 7 is kind of bogged down and slow everything down. And the capacity is only 20 for that reason.
So the capacity is only 20 because that's where the bottleneck
Mm-hmm.
exists.
Exactly.
Are we supposed to show that in some kind of mathematical equation, or is the
No, no,
capacity 20
no,
because
it's
there's
not.
that?
The
Okay.
question is not for the equation or solving and the mathematical. No, it's just you're analyzing how this system work and see what to think of the system.
And then
No.
for B,
Mhm.
you're just asking our opinion on what we would think it should be increased to in order to increase the output of the system.
Right. So looking at this example and which operation should be and looking at this station, those two rows
Mhm.
and coming down to 7, then, which station must be increased, the output, so that it can go flow better. This is, I think it's 7 or 8 or 6 or 5. If you're going over to the left side, maybe it's kind of arbitrary because it's, pretty much same thing, but that might not be answer,
Well, that definitely makes sense to increase where the bottleneck exists
Exactly, yeah.
to the sum of the 3 and 6 so that it can handle it.
Exactly, yeah.
If not a little bit more, just in case.
Yeah. Well, this one is pretty simple one, and just again, this is not for the calculation, but the understanding of a bottleneck. So.
All right.
Any other questions?
No.
We good? All right. So again, if you have any questions, problems, just give me an email. So I'll try to help you out quickly.
With regards to the exam and the 2 questions, when should we expect to be able to resubmit those?
Again, as soon as I finish the grading, I'll post it.
Oh, okay. I'm sorry.
Yeah,
okay.
I'll post it. Okay, so that you can submit your answers and all that.
Perfect. Thank you.
Okay. All right. So have a nice day, and we'll see you next week.
All right. Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.